Okay, and then we go to basic renewal theory. So now we've set the scene, and now we can go into the theory. So we say that traditionally it was assumed that both scheduled reconditioning and scheduled replacement leaves the item in the good as new condition after preventive action, and the theory called the renewal theory developed around this premise. In other words, the renewal theory is the theory that explains failure situations where use-based preventive actions lead to complete restoration. This theory can be approached from different angles using different mathematical theory bases. Often it's approached from the side of statistical distributions. You must stop me if you in any way start missing me or losing me. It's generally accepted that failures where the renewal assumption, this assumption whole, takes place according to some other distribution. You remember when we looked at the density function, it's a sort of a statistical distribution shape. So that's what we're talking about. The one that is used most often in maintenance work is the Weibull or the Weibull distribution, named after the author of the distribution, Swedish guy Weibull. It is a very versatile distribution that can simulate most failure situations found in maintenance practice. The Weibull distribution was the result when Weibull in 1951 suggested an empirical formula that could handle most real-life failure data. So it was an empirical formula. He looked at the problematics and he found that not one of the existing distributions could really handle everything. So he tried to find something that can handle all or most, at least most, failure situations. Most important for the purpose for our purpose is the fact that it can handle all the more frequently encountered shapes of the hazard function. And that is what is important to us, because we've now looked at this decreasing function, constant function, increasing function. One wants something that can do all of that. This leads to the possibility of using only this one distribution for most practical failure analysis applications. Now we say that there are two forms of the Weibull distribution, a 2-parameter version and a 3-parameter version. Now maybe just by introduction to those two distributions, the 2-parameter version just looks at the shape of the distribution or the shape of any of those functions. You remember we have these 4 functions, the density function, the cumulative distribution function, the survival function, and the force of mortality function. Now, all 4 of them, the shape is affected by one of the 2 parameters of the 2-parameter Weibull. And the other one is the scale, the time scale, the use scale. Okay, so those 2 things are included in the 2 parameters. The 3-parameter has one extra parameter, and that is where you find a component or a unit that never fails before a certain age. In other words, this thing always lasts up to 2,000 hours. It will never fail before 2,000 hours. Then that same those same functions are moved along the x-axis to 2,000. So, like the density function only starts at 2,000, like that. And then you get a 3rd parameter called the now I don't remember. We'll get location. I'm sorry? Location parameter. There you go. The location parameter. The use of the Weibull distribution is by estimating values for its parameters such that the distribution closely resembles the distribution of time to failure found in the observed time. The 2 Weibull distribution parameters for the 2-parameter version is beta and eta. And there you have your various functions. So there you have your density function at the top left, ft. And then you have your cumulative distribution function here, your survival function, and your force of mortality function. And all of that, of course, can be calculated from using the density function from the basic definitions. So like this ft, you would say ft equals the integral from minus infinity to t of ft dt, and you replace ft with that ft there, and you get this one. And then rt equals 1 minus ft, and then you get that, and this one is ft over rt, and you get that. Now, okay. Now, what is now very important is to say, well, okay, the moment that we understand we have the parameters beta and eta, then we have the function. So when we get a certain failure situation, then what we need is we need the beta value and the eta value for that situation. So we have a certain component, and we have failure data for that component, for a certain failure mode of that component. And we have this failure data, and from that failure data, we now want to estimate what are the values of beta and eta, because then we have something that we can work with. So, what we do is we make use of that ensemble of formulas, those two formulas. We say these two equations are used to estimate the values of the two parameters beta and eta, such that the resultant V-Boole distribution in most cases accurately represents the original failure data. Now the left side of the top equation has a constant value for a given failure data set. So you can see that the moment that you calculate that, you take all your failure times, you calculate the natural logarithm of each of the failure times, you add it together, all of them, and you divide it by the number of failure times. So that left-hand side is a constant thing. So we say the value of beta is then found that causes the right-hand side of this equation to be equal to the left-hand side. Because you will see you don't find eta in there, you only find beta in there. So you just have to calculate the value of, you have to find the value of beta that makes this right-hand side equals to the left-hand side. And then you have the value of beta. And then you simply replace the value of beta in here, and you calculate eta directly. So, and that's fairly easy. So you calculate, you calculated all the ln ti values there. So you just take each of those ln ti values, multiply it by its made in terms of ti to the value beta, to the power of beta. Then you multiply that, and you add all of those multiplications together. Here you take all your ti to the betas, you add them together, you divide it in there, and minus 1 over beta. And the only thing that you have to do is you have to assume a value of beta in this thing, get a value, and then through iteration find the right value of beta such that this becomes the same as that. And you're okay. So we do it in two ways. So by the way, just you can also use a graphical method. So you can calculate for different values of beta, you can calculate the values of that right-hand side. So you can have on a graph, you can have that right-hand side, whether it now goes up or down, I don't remember. But you can calculate that, and you can use a single value cutting through there, because this is a constant. So the point where that graph cuts through that constant line, that is the point. That's what the value of beta is. So you can do it graphically, but the way we do it is we do the following. We put it on a spreadsheet. So we calculate that left-hand side as a fixed number. We calculate the right-hand side by having a in one of the cells we have the value of beta. So we assume a certain value of beta, and we have the right-hand side. It calculates the right-hand side through calculating for the various TIs on the left-hand side. You have columns for ln TI, for TI to the beta, and for TI to the beta ln TI, added up at the bottom, etc. I'll show you just now. And so we do that, and what we then do is we make use of a function in Excel that does that finds the value for you, that do the iteration, and I'll show all of that. And the moment that you have beta is a simple calculation. So that's the one way. The other way is there are many software packages which you can use to do this type of thing. I have a piece of software called MAnalyst, and MAnalyst is available to you for use. You can download it from our website, and then you use that. That makes it even simpler because you just put the data in and it does the calculation for you. Okay, so we'll look into all of that. Or alternatively, we don't look at it, the videos shows you exactly how it happens. Those videos that you can download. I'm not sure whether we do it here, but at least there it's done. So beta is the shape parameter and eta is the scale parameter. Thus, the shape is dependent on beta, and there's the various shapes for various values of beta of the density function. So that's the density function. So you will see that beta equals 1. If you know statistical distributions, it simulates the exponential distribution, which is a distribution widely used in reliability. So it simulates the exponential distribution. In beta equals 0.5 or lower than 1, it simulates the hyper-exponential distribution. And then it simulates various distributions as it goes along, like the gamma and so on. And at around about beta equals 3 to 3.5, it simulates the normal distribution, completely bell-shaped distribution. If you look at the cumulative distribution function, that's how the various how the fields are shaped. So by the way, you will see that these have been drawn for eta equals 1. So eta equals 1, in other words, the scale parameter is used as 1 there. So if the scale parameter was 100, then that thing would have looked just as it looked there, but the scale would have been different. But that crossing point there, this crossing point, would have occurred then at 100 instead of at 1. Right, and the opposite of that, the survival function shapes, and then eventually the force of mortality, shapes. So you see that for beta smaller than 1, it has a decreasing force of mortality. For beta equals 1, it has a constant force of mortality, and then as beta starts moving above 1, it has different shapes of increasing force of mortalities. At beta equals 2, it has a force of mortality that is directly proportional to the U scale. When it is between 1 and 2, it has a convex, what I call a convex shape. And when it's larger than 2, it has a concave shape. We say the time scale depends on eta. Eta is also called the characteristic life of the component. Characteristic of life. Thus, the typical life that one would expect from such a component, based on past history, is eta time units. Another important feature of the value eta is that 63% of all components of that type will fail before eta time units and 37% after that. You can see it here when you get here and you look, for instance, at the survival function here, you will see 37%. At 37%, you have this covered. So 37% will survive past that life, and the opposite of that, 63%, will fail before we're at that life. That says nothing about when do you have to replace, when do you have to reuse permanent. Nothing. You have to add money, economics, before you can come to that conclusion. So this says nothing more than 63% and 37%. And the reason why it's 63% and 37% is simply because the mathematical E function plays such an important role in reliability. So it's a function of E. That's why you get it. As we saw, it's only for figures for values of beta larger than 1 that we would expect use-based preventive maintenance to be worthwhile. You know, because you have an increasing portion of that. Are you okay with it? You're quite slow with that, with those reactions.
Maybe it's something for a further later discussion, but other than specifying the very first, let's call it inspection, for a new component or a new system, there's no need to specify any other use-based tool. And with that include time and whatever other measure you use, or condition-based inspections. Because as this failure happens, these failures happen, they will determine beta and eta values for you, even if you've got enough data. So a human need not specify how often a valve needs to be replaced or whatever, other than the very first time. Is that correct?
To a large extent. To a large extent. In the reliability-centered maintenance, you will find that when you have enough historic information, and now I'm talking about historic information, not about the specific component or the specific system, but about similar components, similar systems in the past, then you could specify a start-off value. The start-off value is normally a very conservative value, because you want to make sure that nothing bad happens. And then as time progresses, you sort of learn, you go through a learning experience, and you start modifying your initial set, your initial specification. And very often then, the moment that you have enough failure data, you can of course do a full analysis of that, and then you can get even a better answer. So that's the idea.
So unless you're redesigning or designing new components all the time, all you need access to is, let's call it a database of historic failure rates of same or similar equipment.
Using the wrong term. Failure rate.
Sorry, that comes from maintenance practice 1, by the way.
I know. But I'm not saying that all people at Turkish understand this. I mean, I can name much bigger people in the world that doesn't understand this. So don't be worried about Turkish lecturers that don't understand. because it's a tough cookie to crumble. I can tell you that of a class this size, when we're finished, there might be 1, 2, 3 students that will completely understand. It's really tough to understand the full impact of all of this. Okay. Thus, the first important function of failure data analysis is that only when we know that our data's failure of force of mortality is increasing with time, will use-based preventive maintenance be effective. So what we're saying is the first thing that we want to find out, do we have an increasing force of mortality? Yes or no? That's one of the most important questions in one's mind. Because only then can you practice use-based preventive maintenance. Of course, let me just say, in all cases, it's better to practice condition-based preventive maintenance if you can. If it's practical, if you can measure things that will tell you when things will go wrong, if it will reduce your risk to low enough, of course, then condition-based maintenance is the better one. We said that from the beginning. The problem is that you cannot always use condition-based maintenance. So, in cases, the moment that you have to consider use-based maintenance, then your first question is, do I have an increasing force of mortality? Because if you don't know that, you cannot practice use-based maintenance. Then use-based maintenance is out of the question for you. You cannot use it. You must know what is the shape of your force of mortality. We say, but an increasing force of mortality is not a guarantee that use-based maintenance will be worth the expenditure. Because even if you have an increasing force of mortality, the economics might not make sense. Now some people say, well, okay, if it's such a small percentage that use-based maintenance is usable, why do we have to go through all this pain? The answer is simply, there's a few answers. The one answer is that you often find units where you cannot use condition-based maintenance properly, where you cannot do anything else, and which are very expensive units in terms of production loss when it fails, or the cost of the thing itself to repair it when it really fails catastrophically. So very often you sit in situations that you just need to use use-based maintenance. You just need to do the analysis. So that's the one answer. The other answer is that by doing this analysis, you understand your failure mode so much better. Even when you use condition-based maintenance eventually, you understand things better. So deciding how often to do condition-based inspections or condition-based condition monitoring analyses, it's just better. Just better if you understand it properly. So it's something that one has to go through. If you're a maintenance person, you must do this. You have to do it. It's responsible. You do it. Okay, so something else on the vehicle distribution. And we do not know how often should we do the use-based preventive maintenance. We do not know how often. These answers we will now answer in the next question based on economics.